The Neuralink Elon Musk American neurotechnology company makes this brain module. It is one of the first ultra-high bandwidth brain-machine interfaces to connect humans and computers, and it uses flexible electrodes thinner than a human hair to connect the module to the brain. Recently, Neuralink demonstrated a working model of this link device. The model is called Link V0.9. Each link has 1,024 electrode channels with read-write capacity. Alternatively, the system could include as many as 3,072 electrodes per array distributed across 96 threads, each 4 to 6 micrometers in width. This module measures 23 millimeters by 8 millimeters, and it fits flush with the skull so it becomes almost invisible. It has a megabit wireless data transfer rate with post-compression, and the battery can run for an entire day on a single charge. And it can be recharged inductively and wirelessly like a smartwatch. The module has sensors for temperature, pressure, movement, and electrical activity, and also comes with a 6-axis IMU. An IMU is an inertial measurement unit. It is a specific type of sensor that measures angular rate, force, and sometimes magnetic field. The brain module wirelessly receives information from thin, flexible electrode threads embedded in the brain. A robot will be used to surgically implant these threads. The robot will open the scalp, insert hundreds of these thread electrodes, and also place a computer chip while avoiding the surrounding blood vessels in order to minimize the necessary bleeding and damage to normal brain tissue. However, over time, these electrodes have the side effect of activating non-neuronal cells. These non-neuronal cells, of which there are more in the brain than neurons, the astrocytes, the oligodendrocytes, and the microglial cells, tend to form a sheath around the electrodes, thus preventing them from touching the very neurons from which they were intended to record. Other problems that may occur include infection, inflammation, and follow-up surgery to adjust the positions of the electrodes. Millions of individual cells, the neurons, are much too small to be observed and checked individually by the current technology of this brain module. Its electrodes are still too large. Therefore, only groups of neurons can be studied at a time. When excited, the neurons give off a sharp pulse of electrical current called an action potential, or spike. So the brain activity produces these action potentials that show up as blue spikes on the screen when a particular section of the brain is stimulated. It is these spikes that are recorded by the electrodes in the brain module. However, only the collective spikes can be recorded and monitored. At present, Neuralink is trying to deal with this problem by using computer programs. But so far, they have not been able to get sufficiently precise and accurate results from the algorithms they've used. To their credit, though, Neuralink's custom chip is able to identify and transmit patterns of neural activity. When neurons fire, these action potentials that they release produce short bursts of electrical activity that stand out from the background noise. Neuralink's chip is programmed with a set of spike templates that correspond to the usual range of patterns seen in the firing of actual neurons. The electrodes record this neural activity as an analog signal. The implanted chip converts the analog signal to a digital one. Then the signals that identify the action potentials are separated from the background noise. These digital data of action potentials are then compared to the stored templates of spikes until the best match is found. That allows the chip to transmit a code that identifies the template, making for a huge compression compared to the complicated, noisy neural activity. This is absolutely necessary for a device that will be communicating via a low-bandwidth interface like Bluetooth. The brain module will also allow the electrodes to be used to stimulate neurons. At present, Neuralink's brain device has approval from the FDA for limited human testing. They have to follow FDA guidelines for testing medical devices that are considered breakthrough devices. If it works, the device may be able to assist with the treatment of medical problems related to memory loss, addiction, strokes, heart attacks, amputations, spinal cord injuries, and perhaps many other complaints where the nervous system is likely to play an important role. Eventually, the surgical placement of the Neuralink device would be safe enough and quick enough to be completed in less than an hour without using general anesthesia. It is possible that the first clinical trials of the device may begin this year in 2020. The first patients are likely to be those with spinal cord injuries, and therefore they may require 2 implants, one in the brain and a second in the spine. In the future, a device like this can probably be used to improve the functioning of a normal human nervous system. Of course, a lot of this has its roots in science fiction. Elon Musk, the man behind the Neuralink Corporation, was influenced in part by Ian M. Banks, a science fiction writer. Banks wrote 10 novels about the culture of fictional universe, in which a digital neural lace was placed above the brain's cerebral cortex to create a brain-computer interface and achieve a kind of symbiotic relationship between human and artificial intelligence. With an efficient and seamless physical brain-computer interface, normal humans would be able to increase their cognitive abilities. For example, most people have become dependent on the increased availability of information supplied by a smartphone. In the future, access to this information could be directly available to the brain via an implant. Amputees who have lost either an arm or a leg have long been able to replace these limbs with artificial ones called prosthetics. Today, there are neuroprosthetics that relay brain signals to these artificial limbs so that disabled people can have more control over their movements. With Neuralink's new developments, it may be possible in the future to make neuroprosthetics that can control movement and also interact with external devices via broadband internet connections. So the ultimate purpose of this technology is to physically unite the human brain with artificial intelligence in both structure and function. Brain-machine interfaces, BMIs, have been implanted in humans since 2006, so this concept was not started by Neuralink. Neuralink's developments were to have electrodes made of thin, flexible wires that can detect the activity of neurons. These flexible wires create a larger number of electrodes than those found in other systems. This, of course, means that more information can be detected and recorded. In addition, because of the small size and the flexibility, these wire electrodes do not do as much harm to the surrounding brain tissue as would normally be found with stiffer recording needles. And their small size will allow more implants via capillaries and will enhance their ability to detect the brain's electrical activity in a more focused and precise way. Nevertheless, any foreign object placed permanently in the brain will eventually degrade over time, and eventually, smaller foreign objects tend to degrade even faster. This makes it difficult to create an implantable device that can survive and function for several years over the course of a lifetime. Recently, on August 28, 2020, there was a demonstration of the new Neuralink brain implant. 2 pigs were used in the demonstration, one with the implant, Gertrude, and a second without an implant, Dorothy. Gertrude has carried the device for 2 months in an area of the brain linked to the snout. Dorothy used to have an implant, but it was removed. She was there to demonstrate that an implant can be safely removed without bringing any harm to the subject. Gertrude, with her module still in place, moved around the pen while electrical activity in her brain was recorded and displayed on a monitor. The electrical activity came from the neurons connected to the pig's snout. A pig's snout is very sensitive, so a comparatively large part of the brain is involved in its function. The implant was able to record the action potentials in the brain as they were being fired from the stimulation induced by the activities of the snout. These action potentials produce a series of dots and noises that can be observed and monitored on a computer screen. The main purpose of the demonstration, however, was not only to show what progress had been made, but it was also intended as a recruitment exercise to attract attention and get more people involved with the Neuralink Corporation. There is a need for neuroscientists and engineers in the fields of software, robotics, and electronics. At present, there are approximately 100 people working at Neuralink. The desired number is closer to 10,000. Since its inception, there have been some difficulty retaining employees at Neuralink. The company has hired many prominent neuroscientists since it started, but has struggled to keep them on staff. For example, only 2 of the original 8 neuroscientists that started with Neuralink in 2017 are still with the company. The Neuralink Corporation was founded in July 2016 by Elon Musk, Ben Rappaport, Dungeon Seo, Max Hodek, Paul Merola, Philip Sabes, Tim Gardner, Tim Hansen, and Vanessa Tolosa. It was first publicly reported in March 2017. Its primary purpose is to develop and manufacture implantable brain-machine interfaces, BMIs. The headquarters are in the Pioneer Building in San Francisco, California, USA. $100 million was invested into the company by Elon Musk, and another $58 million came from other sources, for a total of $158 million as of July 2019. In addition to leading Neuralink, Musk is chief executive of Tesla, an electric vehicle business, SpaceX, a reusable spacecraft manufacturer, and Boring Company, which is building tunnels to reroute vehicular traffic from dense city centers. In addition to physical applications, the Neuralink device has the potential to help in the treatment of mental illnesses such as depression and anxiety. These diseases are very common, so there is a great need for effective therapies. There are over 40 million people, men and women, over the age of 18 who suffer from anxiety and depression in the United States, and of those who are affected, only 36.9% receive treatment. There are a lot of very strong prescriptions available, but many of these have unpleasant side effects, and some can even hurt the patient. Other medications can also lead to various sorts of addiction or dependency. The Neuralink brain implant can temporarily help to alleviate the effects of these mental illnesses until the patient can seek more definitive treatment. The implant can lift the mood of a depressed or anxious person and thus motivate them to want to improve their condition. In theory, therefore, Neuralink could provide an affordable, short-term bridge to treatment for those who simply do not have access to what they need. This temporary panacea could stem the tide of debilitating mental illness and thus help prevent the increasing number of suicides that may inevitably result. Green, writing in TNW, the Next Web, was not impressed with Neuralink. He called Elon Musk's August 28 demonstration stupid, and concluded that the future could be bright for Neuralink, perhaps one day it'll live up to its hype, but it's doubtful whether that'll happen in Musk's lifetime. There's nothing solid to support the idea that a simple implant can suddenly turn the human brain into an OS-accessible database, ready for read-write functionality from a classical computer. At the end of the day, Neuralink is another example of Musk's hype machine getting everyone excited for science and technology, only to remind us that optimism and money aren't the only things keeping humans from living in a science fiction utopia.